Welcome. So the topic we'll be discussing in this lecture is binary search trees. Okay. So basically we'll be discussing like what is a binary search tree and how it differs from a normal binary trees. We will define binary search trees and then we'll be discussing how to create a binary search tree through a C program, how to perform insertion in a binary search tree, what is the actual logic and how to implement that. Then we'll be discussing how to search an item in a binary search tree, what is the logic and how it is implemented. And also we'll be discussing about how to delete a node from a binary search tree. Okay. So these are the concepts that we are going to discuss in today's session. So before that, when you search a binary tree, how will you search a binary tree? The binary, if you want to check whether a particular node with a so and so key value exists in the binary tree or not, if you want to do that, how will you do that? You have to traverse through the binary tree. Okay, so you can traverse in any one of the three ways which we have discussed, like pre-order traversal or in-order traversal or post-order traversal, and then you can check whether a given node is present in the binary tree or not. Okay, or you can also use level order traversing, another traversing technique which we have discussed, or you can also use level order traversing and you can check whether a node exists or not. Say for example, I want to check whether this node 9 is in the tree or not. Then start from the root node and move from left to right. Is 2 is equal to 9? No. Then go to next level because there is no more nodes in this first level. So the leftmost node is 7. Is it equal to 9? No. Then the next is 5. Is it equal to 9? No. Then go to the next level. Here the leftmost node is 2. Is it equal to 9? No. Then the next node is 6. Is it equal to 9? No. Then the next node is 9. Is it equal to 9? Yes. So you can now reply that yes, the node is available, and you can stop here. Okay. But what you can observe from this searching technique, could you say that this is better than searching a value in a linked list in the worst case scenario? No, it is not better, because assume that here we are searching for 9. If you want to search 4, then you have to search all the nodes, then only you will find the fourth node. Okay, so if there are n nodes in this binary tree, if you want to find out whether 4 is there or not, you have to search all the n nodes, then only you will find the you can ensure that 4 is there or not. Okay, as fourth node is the last node. So this is the worst case time complexity for this. Okay, this is same as that of linked list. In linked list also, say if there is a node, if there is a key in the last node, if there is some key value in the last node, and if you want to check whether that particular value is exist or not, in a normal single linked list, then you have to go through every node from first node to last node, then only you can find that, right? So the worst case search complexity in a linked list also it is order of n, in binary tree is also it is order of n, right? So is there any way to reduce that? Yes. So binary search tree is one of the technique where searching can be done in a less time. Okay, fine. So let us understand what is a binary search tree. So first of all, binary search tree is a binary tree. Okay, first is binary search tree is a binary tree, right? So it should be a binary tree, that is every node can have at most 2 children. No node can have more than 2 children. Okay, either it should have 0, 1 or 2 child, not more than that. Other than that, it has two important properties. One is that the left subtree of a given node will have always less value than that particular node. Okay, we will call it as key value. Let us say that this particular node has a key value of 5. If you take the left subtree of this particular node, or for all these nodes, the key value will be lesser than this. This may be 2. Okay, right? But if you take the right subtree of a given node will have a value which is greater than the key value of that particular node, so this may be 7, right? Okay, similarly if you take this 2, its left subtree or its left child will have a value which is lesser than that, maybe 1, but its right child may have a value greater than that, so 3. Okay, but put together if you see the all the left children of I mean the key values for all the nodes in the left subtree of node 5 is lesser than 5. Okay, this is applicable here also, right? So if 7 has maybe here 7 may have another node 6 as a left child. Okay, but 6 is still greater than 5. Okay, so it is in the right side of 5. Okay, 6 is, if you see 6, it is greater than 5, but it is less than 7, so it is in the left side of 7. Okay, so such a binary tree is called as a binary search tree. That is for a given node, its left child will have a value which is lesser than the key value of that particular node, and its right child will have a value which is greater than the key value of that particular node, right? And one more thing, the key values for every node, for all the nodes in a given binary search tree should be unique. Okay, the key values for the nodes in a given binary search tree should be unique. That is, a binary search tree cannot have duplicate values. A binary search tree cannot have duplicate values. So this is how we define binary search tree. Okay, so the value stored at the node, okay, at a given node is greater than the value stored at its left child, and the value stored at the given node will be less than the value that is stored at its right child. Okay, so this is the important property of a binary search tree, and also the key values should be unique. Fine. Okay, so the value stored at the root of a subtree, so if you take the root of the subtree, is greater than any value in its left subtree. Okay, it is greater than any value in its left subtree, and the root value will be less than any value in the right subtree. Okay, normally we use integers, but if you see this diagram here, alphabets were used, but alphabets were numbered, like starting with A equal to 1 and Z is equal to 26. Okay, so in that context it is taken. Okay, so if you see the root of this tree is E, then C, which is less than E. Okay, A is less than C, but D is greater than C. B is greater than A, so it's the right child of A. Okay, H is greater than E, so it's the right child of E. F is less than H, so it is the left child of H. I is greater than H, so it's the right child of H. G is greater than H, so it's G, if you see it's greater than E. Okay, it is greater than E, but it is less than H. Okay, but it is greater than F. Okay, A, B, C, D, E, F, G, H. Okay, so it is less than H, it is greater than G, so it comes here. Okay, if you see I is greater than H, and J, so it is coming in the right side of H, and J is greater than I, so it is coming in the right side of I. Okay, so the point is, in a binary search tree, if you take typically any node, its left child will have the higher value than that particular node, and its right child will have a lesser value than that particular node. Okay, fine. Yeah, so you can see this is also a binary search tree. Okay, it's a binary search tree, right? It's not a binary tree. I think previously somewhere I said binary tree. This is also a binary search tree. So if you see the root is 4, the root node is 4. If you see the left, its immediate left child, it is 2, which is lesser than 4. And if you see its immediate right child, it is 6, which is greater than 4. And again, if you take 1, the left child of 2, it is lesser than 2, and the right child of 2, it is greater than 2. Okay, but this entire subtree, if you see all these values 1, 2 and 3, all these are lesser than the value of the root node, or the key value of the root node. Okay. Similarly, if you see the left child of 6, it is 5, which is less than 6, and if you see the right child of 6, it is 7, which is greater than 6. Again, if you see the, if you take the right subtree of 4, it contains these nodes 5, 6, 7, which is greater than the root node. Okay, so this type of tree is called as a binary search tree, right? Okay, fine. So where will be the smallest element in a binary search tree? So surely the smallest element will be in the left subtree. It will not be in the right subtree. Okay, the smallest element will be in the left subtree. Okay, and again in the left subtree, where it will be? So surely C is lesser than E. Okay, and C is lesser than E, and A is lesser than C. Okay, so in the left subtree, in the leftmost, it will be there. Okay, okay, right? So this will be the smallest value, right? And where is the largest element? The largest element will be surely in the right subtree. It will be surely in the right subtree. So if you see this, E is greater than H, sorry, H is greater than E, and I is greater than H, and J is greater than I. So this will be the largest element. Okay, so the point is, if you want to identify the smallest element, you start from the root node and just travel towards the left until you reach the last left node, further which there are no left children. So that will be the smallest value. Okay, similarly, if you want to find the largest value, start from the root and travel in the right side. Go to the first right child, go to the next right child, continue this process until you reach the last right child. Whichever is the last right child, that will be the maximum value, right? And whichever the node which is the left, whichever the node which is the last left child, that will be the smallest value. Okay, so these are some of the advantages of binary search tree, right? And as the name says, it is a binary search tree. It makes searching much easier. I mean, it reduces the complexity of search. Okay, so where is the smallest element? It is in the leftmost. Okay, and where is the largest element? It is in the rightmost, right? Okay, so how to search a binary search tree? How will you search whether a particular element is present in the binary search tree or not? Say for example, I want to find whether I is there in the binary search tree or not. So how do I do that? Start with the root node. Start with the root node. Okay, and check whatever you are having. E. So is E is less than I, or you start or you compare whether I is greater than E or less than E. Whatever you want to search, that you compare with the root node. Is it greater than E or less than E? It is greater than E. So greater than E means go to its next right child, which is H. Again compare this. Is I is greater than H or less than H? Is greater than H. So again go to its right. Okay. Okay. Again you check. So first after coming here, you have to check whether this is I or not. Yes, it is I. So stop. Okay. So initially also like that only. You start with the root node and check whether is this I or not. No, this is not I. Then check whether I is less than E or greater than E. If I is less than E, go in the left side. Otherwise, go to the right child. I is greater than E, so go to the right child. And if you go to the right child, you get the node H. So again check whether H is equal to I or not. H is not equal to I. So again check whether I is less than H or greater than H. I is greater than H. So again go right. So you reach this node. Again now you check whether is this equal to I. Yes, it's equal to I. So now you can say that the node is available. Actually this will reduce the number of searches which is performed, because at first go itself you are able to discriminate whether the value is in the left subtree or in the right subtree. Okay, so by that what happens, the amount of search will be reduced to a greater extent. Okay, and in every node we are differentiating the path, whether it will be in the left subtree or in the right subtree. Okay, right, fine. Say for example, if you want to search B, then how we will search? Start with E. Okay, is E is equal to B? Is E is equal to B? No, E is not equal to B. Then check, is B is less than E or greater than E? B is less than E, so go to the left child. Left child is C. Is C is equal to B? No. Is B is less than C or greater than C? B is less than C. So again go to the left child. Left child is A. Is A is equal to B? No, A is not equal to B. So again check whether B is less than A or greater than A. B is greater than A. So go to the right child of A. Right child of A is B. So you have found out. Okay. So the time complexity will be reduced when you are using binary search tree. Okay. So whatever I have told, that's what explained here. Okay. So when you see, so searching a node in a binary search tree, is this better than searching a linked list? Yes, it is better than searching a link. So yes, it is better than searching a linked list. Here the worst case time complexity will be order of log n. Okay, it will not be order of n, it will be order of log n. Okay, whereas in a normal binary tree also it is order of n. In normal binary tree also it is order of n, but in a binary search tree it is order of log n. Okay, that is what in the first slide we have discussed. If you recollect, a normal binary tree is no better than a linked list. Here also, with respect to searching, here also it takes order of n times. Okay, whereas in a binary search tree, the searching speed can be increased. Okay, because we are dividing the tree into two subhouse based on their values, right? Okay, fine. Okay, so this is how you can define a node. Fine, that coding part we will discuss later. So that as usual it is a binary node, there will be one data part. Okay, and there will be two pointers, one pointing to the left child and another one pointing to the right child. Okay, the implementation will come. I will not discuss these programs now. Okay, before that we will discuss sometimes later. Okay. Okay, so let us see how to insert something into a binary tree, right? Or inserting or creating a binary tree, almost same. So let us see how to insert something in a binary tree. So initially let us assume the tree is empty. Initially assume that the tree is empty. Okay, that is or assume there is a pointer tree, it is pointing to null. There is a pointer tree, it is pointing to null. Okay, this is null and this is the pointer, right? Now you are going to insert one element 5. So before inserting you check whether tree is equal to null or not. Yes, tree is null, so there is nothing in the tree, so nothing to check. Make this pointer to point to this node 5. So you create a node 5 and make it to point to that, right? Okay, next we want to insert a node 9. Okay, so now the tree is pointing to 5, which is the root node. So the new node which came in is 9. Okay, so you check. So let us assume the inputs are unique. Let us assume the inputs are unique. Otherwise you have to check whether actually it is a unique number or not. If it is already there, you should not insert. Okay, so let us assume the inputs are unique. So it just checks whether 9 is less than 5 or greater than 5. 9 is greater than 5, so it will be added as the right child of 5. So 9 is added as the right child of 5. Okay, next there is another input 7. So again same process, start with the root node 5, check whether 7 is greater than 5 or not. Yes. Okay, if 7 is greater than 5, then go to its right. What is its right child? 9. Is 7 is greater than 9 or less than 9? It's less than 9. Okay, so is there anything to the left of 9? No. So add 7 to the left of 9. Add 7 to the left of 9. Okay, next we want to insert 3. Okay, so how do we insert? So when 3 comes, this is the tree. Okay, so let us see here, let us check here. Okay, because this is the previous tree, right? This is the updated tree. So let us see here. So 3 is the input. So start with the root node. Is 3 is less than 5 or greater than 5? 3 is less than 5. So where should you go? To the left. Is there anything left of 5? Nothing. There is no nodes to the left of 5. So just add 3 to the left of 5. That's it. Okay, so that 3 comes here. This is the resultant tree, right? Okay, next we want to add 8 to this tree. We want to add 8. So how will you add? Input is 8. Check whether 8 is less than 5 or greater than 5. It is greater than 5. So move to the right. Right is which node? 9. Again check whether 8 is greater than 9 or less than 9. It is less than 9. So move left. move left, again check whether 8 is greater than 7 or less than 7. 8 is greater than 7, so add 8 to the right of 7. Add 8 to the right of 7, so 8 will come here, right? So this is the resultant tree. This is the resultant tree, right? Okay. Again we want to add 12. Again we want to add 12 to this particular tree, right? So start with 5. Check is 12 is less than 5 or greater than 5? Greater than 5. Move to the right child. What is the right child? 9. Again compare, is 12 is less than 5 or greater than 5? Sorry, is 12 is less than 9 or greater than 9? It is greater than 9. So we should go to the right. Is there any right child? No right child. So just add 12 to the right of 9. That's it. So 12 comes here. Okay, right? Next we want to add, say, 16. 6 to this particular tree. So the new node to be added is 6. Compare 5 with 6. Is 6 is less than 5 or greater than 5? Greater than 5. So move to the right, which is 9. So 6 is less than 9 or greater than 9? Less than 9. So again move left, which is 7. So again check whether 6 is less than 7 or greater than 7. Less than 7. Is there anything to the left of 7? No. So just add 6 here to the left of 7. Okay. So this is the resultant tree where 6 is added here. Now we want to add 14 to this tree. Okay. Sorry, 4 to this tree. Okay, to this tree. So check 4 is less than 5 or greater than 5? Greater than, it is less than 5. 4 is less than 5. So move to the left. Left node is 3. Again compare 3 and 4. Is 4 is less than 3 or greater than 3? It's greater than 3. So is there anything to the right of 3? Nothing to the right of 3. So just add 4 to the right of 3. So 4 comes here. This is the resultant tree, right? Again, if you want to insert 20 to this particular tree, again the same process. Compare 20 with 5. Is 20 is less than 5 or greater than 5? Greater than 5. Move to the right side, right child, which is 9. Again compare, is 20 is less than 9 or greater than 9? Greater than 9. Once again move to the right child, which is 12. Again compare, is 20 is greater than 12 or less than 12? It's greater than 12. So add 20 to the right of 12. Okay. So this is what the resultant tree you are getting, right? Okay. So this is how insertion takes place in binary search tree, right? Okay. So insertion can also be done recursively, or it can be done using a normal function. Okay, fine. So all this code we'll discuss later. Okay. So there is a question here. It's quite interesting. Certain orders. There is a question. The question is: does the order of inserting elements into a tree matter? Yes or no? What do you feel? Yes, it matters. Okay. The order of inserting elements into a binary tree, it actually matters. Okay. If the order of inserting the elements is not proper, then the binary tree may be skewed in one direction. Okay. So the answer is yes. Certain orders might produce unbalanced trees. Okay. Certain orders might produce unbalanced trees. What is unbalanced tree? That we will discuss. The actual definition of unbalanced tree we will discuss sometimes later. But as of now, you understand that unbalanced tree means there is a lot of difference between the left subtree and the right subtree. Okay. So maybe the tree is skewed in one direction. Such a tree we call it as unbalanced tree. Okay. So we will discuss with an example. Let us see. This is the order of input which you are giving for a tree. That is first D, then B, F, A, C, E, and G. Okay. So what will happen? So if you draw the tree for this, first you will get D. Okay. D becomes the root node. Then B is where B will come. B is less than D. B is less than D. So B will come here, right? B will come here. Again F. So when you see F, compare with the F. F is greater than D. So F will come here. Okay. Next A. A is less than D. So go left, which is B. Left child is B. So again if you check B, A is less than B. So it should go left, but there is no left child. So here you can add A, right? Next is C. Is C is less than D or greater than D? Greater than D. It is less than. it is less than D, so go left, which is B. With B, if you compare, C is greater than B, so it should come to the right. To the right there is no child, so add C here. Okay. Similarly, next is E. Is E is less than D or greater than D? It's greater than D, so go here, which is F. Compare with F. Is E is less than F or greater than F? It's less than F, and there is no left child for F, so add E to the left of F. Next is G. Is G is greater than D or less than D? It is greater than D, so go to F. Again compare with F. Is G is greater than F or less than F? It's greater than F, and there is no right child for F, so put it here. Okay. So this is how you got this tree, right? But if the input is different, but if the input is something, so when the input is in this order, you got a tree something like this. Okay. But if the input order is changed, if you see the values are same, but if the order is changed, then you will get a tree something like this. So here the first element inserted is B. Okay. Then A is less than B, so it comes here, right, to the left of B. Then D is greater than B, so it comes to the right of B. Then C is greater than B, so you have to go to the right, which is D, but it is less than D, so you have to go to left, so C will come here, right? Again G is greater than B, so go right, which is D. Again G is greater than D, so go right. There is no node as of now, so add G here. Again F is so you have to always start with root. F is greater than B, so go to the right child, which is D. Again F is greater than D, so go to the right child, which is G. Okay. F is, when you compare with G, F is less than G. At this point of time there is no node here, so add F here. Okay. Similarly, when you take E is greater than B, so go to the right, which is D. Again E is greater than D, so go to the right, which is G. Again E is less than G, so go to the left, it is F. Again E is less than F, so here as of now there is no node, so add here E, right? See, the inputs are same but the orders are different, so you got this type of tree. Okay. But if the inputs are something like this, A, B, C, D, E, F, G, if it is in ascending order, then you will get a skewed tree. So this tree, you can see it is skewed in right side. Okay, it is skewed in right side. Okay, so actually the balanced binary tree will perform better. Okay, if you see this tree, it is very much balanced. It is highly balanced, the left and the right subtree, right? Okay, so the order of the elements do matter. Okay, if the order is not proper, then the binary tree may be skewed in one direction. Okay, right? Fine. Okay, so next what we will be discussing is how to delete a node from a binary tree. How can we delete a node from a binary tree? So deleting a binary node, how will we delete a node from a binary search tree? How we will delete a node from a binary search tree? So deleting a node from a binary search tree, actually we will be discussing in three cases. First is deleting a leaf node. How will you delete a leaf node? Second is deleting a node with only one child. Okay, that means you want to delete a node which has only one child. First is leaf node, that means you want to delete a node which do not have any child. Second is deleting a node with one child, and third is deleting a node with two children. These three cases we will be discussing. Okay. First case, say this particular binary tree, assume you want to delete this node Z. So if you see this Z, it does not have any child, not even a single child. It's a leaf node. So just delete it. Just remove the space allocated to it and make the right child of R2 point to null. That's all. Done. Deletion. As a result, you got this particular tree. Okay. Now if you want to delete a node with one child, say you want to delete the node R. Okay. So but R is which child of Q? It's the right child of Q. Okay. And there is another right child for R, which is Z. So just make Q to point to whichever the child of R. Okay, just make Q to point to the child of R. The child of R may be either left child or right child. Okay, just make Q's right pointer to point to the child of R. Okay, that may point either to the right child of R, or it may be either to the left child. Okay, anywhere, right? That's it. So this is how deletion with a delete. If this is how you will delete a node which has only one child. Okay. So the resultant tree will be something like this. So this is the resultant tree that you got after deleting. Okay. Next is deleting a node with two children. If you want to delete a node which has two children, take this particular tree. Say that you want to delete this node Q, but if you see Q, it has two children. There is a child L and also there is a child R. In that case, how to do the deletion? Okay. So in that case, if you want to delete a node which has two children, then there are two ways to delete. Then there are two ways to delete. Okay. The first method is what you have to do is you have to find the infix successor of Q. You have to find the infix successor of Q. What will be the infix successor of Q? So if you see, the infix successor of Q will be, okay, infix successor of Q will be the smallest node in the right subtree. Okay, infix successor of Q will be the smallest node in the right subtree. Okay, you have to find the smallest node in the right subtree and that should be replaced with Q. That's it. Okay, so if you see here, what is the smallest node in the right subtree? Actually R is the smallest node. Okay, so R should come here. R should come here. Okay, but this R should be removed. This R should be removed. So again you have to check. Again you have to, we want to remove this this R is coming here. Okay, we want to remove Q, right? So instead of removing Q, what we are doing is this R is moved here. Okay, but this R should be deleted. Again, how will you delete this R? Again you have to apply all the deletion rule. Check this R is having how many child? Is it having one child or two child or no child? It's having one child. It's having one child. Okay, so just make Q's right pointer to point to the child of R. Q's right child pointer to point to the child of R. Okay, this is one way of deleting. Okay, this is the first way, which is called as identifying the infix successor of Q and then replace that with Q and then delete that particular node. Okay, delete the node by which you have replaced. Okay, again for that node, again you have to apply all the deleting rules, right? Fine. There is another method. The second method is replace Q with the infix predecessor of Q. Replace Q with the infix predecessor of Q. You can replace Q either with the infix successor or infix predecessor. Okay, so what is the infix predecessor? So infix predecessor will be the highest value of the right subtree. Okay. Infix predecessor will be the node with the highest value of the right subtree. Okay, what is infix successor? Infix successor will be the node with the lowest value. Infix successor will be the node with the lowest value in the right subtree, and infix predecessor will be the value with the highest, will be the node with the highest value in the left subtree. Okay, right? So this is the difference between infix predecessor and infix successor. Okay, so Q can be replaced either with infix predecessor or with infix successor. Okay, if you want to identify the infix predecessor, then identify the highest value in the left subtree. Okay, what is the highest value in the left subtree? So in this case, if you see L is greater than Q. Okay, again N is greater than L, again P is greater than N. So this is the highest value in the left subtree of Q. Okay, so infix predecessor means, better I will write, I think I am interchanging left and right subtree while speaking. I'll put it here in words. I'm sorry for that. Okay, so there are basically three cases for deleting. If the node is having only one child, just delete that, nothing else. Okay, and make that parent's left or the right pointer, whatever it may be, that should point to null. Okay, and if the node that you want to delete is having, there are three cases. If the node that you want to delete has no child, then just delete that. Okay, and make the respective parent pointer to point to null. The second case is if you want to delete the node which has one child, okay, then make the appropriate parent pointer to point to that particular to point to the child node of that node which you want to delete, and then delete the node. Okay, if you want to delete a node which has two children, okay, so to delete a node which has two children, to delete a node which has two children, here there are two possibilities. You can follow any one possibilities, but there are two ways of doing that. What are they? The first method is replace the node with the infix successor. Okay, this is the method 1. I'll call m1. Okay, this is method 1. And the second method is replace the node that you want to delete with the infix predecessor. Okay, right. So what is infix successor, you may ask? What is infix successor? It is the smallest node in the right subtree of that particular node. Okay, smallest node in the right subtree of a given node. This is the infix successor. Okay. What is infix predecessor? It is the largest node in the left subtree of a given node. Okay, right. Okay, so here smallest in the sense smallest value. Okay, the node with the smallest value, right? Similarly here largest in the sense the node with the largest value, right? So these are the two ways of deleting a node which has two children. Okay, so first method already we have discussed. Now we are discussing the second method, which is to replace the node with the infix predecessor. So infix predecessor is nothing but the node with the largest value in the left subtree. Okay, so in this case the node with the largest value in the left subtree is p. Okay, so p, first you just replace this q with p, then you have to delete p. Okay, again for deleting p you have to apply all deletion rule. What are the deletion rule? You have to check whether p has how many children. It has one child or two child or no child. It has no child, so you can just delete it, and that appropriate parent the appropriate pointer of the parent should point to null. Okay, that is the right pointer of the parent, which is n, should point to null. So no more this is pointing here, it is pointing to null. That's it. Okay, are you getting? But if this is having one more child, then this pointer should point there. Or if it is having two child, then again for this particular node you have to find either the right either the next successor or predecessor, like that. Okay, right? But that won't happen. This, whatever the node you are finding, no, it will never have two children, it will have only one children. Are you getting? I think you are able to follow. I mean, if you are deleting a node which has two children, okay, then surely you will find a node either with no children or one children to be deleted. Okay, because what you have to find, you have to find the next predecessor or the next successor. Okay, so suppose if there is another child here, then that will become the next predecessor. Okay, so that cannot happen, right? So it may have a child here, but it cannot have a child here. So it will at no case it will have two children, right? Fine. So this is about deletion. Okay, fine. And another important thing I want to say, let me show you one particular this particular diagram which we have seen already. Okay, see, let us try to traverse this particular tree using in-order traversal. Okay, So start from root. This is root. So in order traversal is what? Left, root and right. Okay. First visit the left child, then root and then the right child. Okay. So we'll start with node 4, that is the root node. So does this have a left child? Yes. So go left, which is 2. Does this has a left child? Yes. So go left. Does this have a left child? No. So visit it. Visit. So what will be the output? So output I'm writing here. Sorry. Or I'll write here. Output is 1. Output is 1. Okay. So we have met the left child. We have visited the left, then root. So what is the root of this subtree? Which is 2. So visit here. So 2. Then right. What is 2 its right? 3. Then visit 3. Okay. Now we have visited the left subtree of this particular node. Okay. So this entire left side is visited. So next what you have to visit? Root. So what is the root? 4. So 4. Right. Then where should you go? Right. So go right. Go to the right of 4. 6. Okay. But does this have a left child? Yes. So go left. 5. Does this have a left child? No. So just display that. Just display that. So that is 5. Okay. So we have displayed the left child. Okay. And does this have a right child? No. So this particular node's left is printed, right? Now what should be printed? Its root. So root is 6. So display 6. Okay. Then go to its right. 7. Okay. Does this have a left child? No. Does this have a right child? No. Even though if it has a right child, first you have to print 7 only. So it will be 7. Okay. So if you see the ordering, it is 1, 2, 3, 4, 5, 6, 7. Okay. So which means that when you traverse the binary search tree, in in-order traversal, using in-order traversal, always the output will be in ascending order. Always the output will be in ascending order. Okay. So when you traverse a binary search tree in in-order traversal, always the output will be in ascending order. Okay. You take any tree, you traverse in order, you will get the output in ascending order only, right? So for example, let us traverse this particular tree. If you traverse this particular tree in order traversal, from where will you start? This is the root node. Okay. Does this have a left child? Yes. B. Does this has a left child? No. Okay. So just B. There is no right child. So this is the left child of J. Then print its right. That is J. That is J. Okay. Then go to its right, which is Q. But does this have a left child? Yes. So what is that? L. So L does not have any child. So print that. So now we have visited the left child of some node. So after that you have to visit that node, which is Q. So visit that. Okay. And then go to its right. But does this have a left child? No, it is not having a left child. So there is no left here. So visit that particular node itself. Okay. So that is R. But after visiting that node, where you have to go to its right. That is Z. But does it have left? No. So just display Z. Z, does it have right? No. So here also, if you see, it is in what order? It is in ascending order. B, J. After J it is L, right? Q, R, Z. Okay. So any tree you take, okay, when you traverse any binary search tree, right? When you traverse any binary search tree in order traversal, the output will be always in ascending order. Okay. So when you traverse a binary search tree in order traversal, you can check whether the output is coming in the ascending order or not. Okay. Or if you are creating a binary search tree, then also you can traverse in order and you can verify whether my binary search tree is created properly or not, right? So this is the core about binary search tree. Now I think let us discuss something about coding part. Okay. So fine. So let me take open WSL. I think I already opened, but I think I have closed it. Yeah, let me open WSL. Okay, so I have written the code which is nano bst.c, binary search tree bst.c. Okay, so these are the header files as usual. So here I am defining the node similar way. I'm defining in a normal way, not in the textbook style. Struct node int key, we'll call this as key, and then each node will have two pointers, one to the left child and another one to the right child. Okay, and then we are creating a pointer for root node. Okay, so struct node store root, which is initially pointing to null, right? And then there are many functions. One of the function is insert, okay, which is used to uh, create a node with a given integer value and to insert it into the binary tree. And there is a function called create bst, binary search tree. Okay, there is a function called create bst, which is create a binary search tree. So this will be the function which will be first called by the main. Okay, so main function will first call this, or I'll show you the main function. Yeah, here is the main function. So in main function we are creating an integer and we are creating a pointer to struct node. The first thing what we are doing is we are calling create bst, that will create the binary search tree. So how it is going to create, that we will see. So here we are declaring some variables, okay, and we are declaring some pointers for node, traverse, previous and node. Okay, right? So yeah, so this node is not required, I guess. Again, it's a naming convention problem. This node is not required. Okay, there are two pointers, traverse and previous. First we are asking the user to enter the number of nodes. How many nodes are in the binary search tree? That's what we are asking the user. Okay, and then we are taking that as an input in the variable n. Okay, and then we are so this when this function is initially called, we know that the binary search tree is empty. Okay, so for we are creating a node, okay, and its starting address is assigned to root. Okay, and then for this particular node, what is the key value we are asking? Enter the key value for the root node, and that is read in a variable k. Okay, and then we are assigning like root arrow key is equal to k. So root node we have created here, its key part is assigned with k, and its left child is assigned to null and its right child is assigned to null, because currently there is no left child and there is no right child. So totally how many nodes, that input we have taken here, right? So one node we have created. Like this we have to create remaining n minus 1 nodes. So here we are writing a for loop for I is equal to 2, I less than or equal to n, I plus plus. Okay, because already one node we have created, so we are starting I with 2 and it goes up to I less than or equal to n. Then we ask the user to enter the key for the next node. Then again that is taken in the variable key, and we are calling this function insert of k, okay, which will insert the second node into the binary tree which is already created with one single root node. Okay, so here is the function insert. Okay, so in function insert, if you see, we are declaring some pointers, found, traverse, nod and previous, all these things. Okay, initially we are keeping found is equal to null. Initially we are keeping found is equal to null. Okay, this found is used to check whether one of the property of binary search tree is what? It should have unique values. So you have to check whether the search tree already contain that node or not. Okay, so only if the node is not there, only the node with the given key value is not there, then only you have to insert. Okay, so actually here I have to call the search function. There is a search function here, right? There is a search function. This function will check whether a node with this value already exists in the tree or not. Okay, if such a node exists, then it will return a pointer to that node. Okay, then it will return a pointer to that node, otherwise it will return null. Okay, so in this case actually it is expected to return null. Okay, because then only you can insert the new node. So I'll write here search of s1. It will search whether this particular node s1 exists or not. If it exists, then found will be some pointer, some address. Okay, and this traverse is assigned to root node, then we insert a new node only if found is null. If found is not null, then we won't insert. Okay, suppose if found is not null, then we just say that the node with that particular key already exists, so you cannot insert that again, right? Because it should be unique. If found is null, then we have to identify where it should be inserted. Okay, so if you recollect from whatever we have discussed, for example, say in this binary tree, say for example, uh, there is a lot of clumsiness here. Okay, say, or I'll take another tree. Yeah. Okay, say let us take this particular binary tree. Okay, say for example, in this binary tree, if you want to insert, say, a new node 23, then you have to start with root node, check whether 23 is less than 30 or greater than 30. It is less than 30, so go to the left child 15. Is it less than 15 or greater than 15? 23, it's greater than 15, so go here. Again here 22. Is 23 is less than 22 or greater than 22? Greater than 22, so go to the right child 27. Is 23 is less than 27 or greater than 27? It is less than 27, so it will be inserted to the left of 27. Okay, this process we have to do. So that is what here we are doing. Okay, so what we are doing is traverse is pointing to the root node, and this is the node which we want to insert. So we check, so we know that there is no, as found is equal to null, we know that this is a unique node. Okay, this is a unique node, so we just check whether S1 is less than traverse arrow key. Traverse is root node. Okay, if it is less than traverse arrow key, then you have to go to the left child. Okay, so we make previous equal to traverse and traverse equal to traverse arrow left child. Otherwise what we do is, if S1 is not less than, means it means S1 is greater than traverse arrow key, then you have to go to the right side. So then we say previous equal to traverse and traverse equal to traverse arrow right child. Okay, like that this while loop will continue. How long it will continue? Until you reach, until traverse become null. Okay, when traverse become null, previous will point to that particular node after which the new node should be inserted. Okay, the while loop will come out only when traverse becomes null, but when traverse becomes null, previous will point to that particular node. Okay, previous will point to which node? Previous will point to that particular node, which is previous will point to that particular node after which the new node should be inserted. Okay, so after coming out of the while loop, first we create the memory space for the new node, and a node is pointing there. Okay, and a node is, this is the new node. Okay, and the new node's key will be assigned with S1, and new node's left child and right child will be pointing to null. Okay, new node's left child and right child will be pointing to null. Okay, right, and then what we do, in the sense, here after that we check. So after previous we want to insert, but again there is a question whether it should be inserted as a left child of previous or right child of previous. Okay, so again you check whether S1 is a less than previous arrow key or not. If it is less than previous arrow key, then insert this new node as a left child of previous. So previous arrow left child will be equal to node. Otherwise insert this as a right child. So previous arrow right child equal to node. Okay, and then say insertion done successfully. Okay, so this is the logic to insert a node into the binary search tree. Okay, fine. So like this we insert all the remaining nodes. So that logic is for insertion. For creation also like that we insert all the remaining nodes. Okay, so this is how insertion is done. And traversing, here I have written code only for in-order traversal, which we already discussed. So when you call the in-order traversal, this is just to verify whether everything we are doing properly or not. So if the tree is created properly, then you will get the output in the ascending order, right? Okay, right. Okay, so then to search, this is the logic for searching, which is used to check whether a given node is in the tree or not. So we pass a node yes, right, and we want to check whether it is in the tree or not. So here we have some pointers, make traverse to point to root, and then start checking. So while traverse, it means while traverse not equal to null. This just means that while traverse not equal to null, you just check. Initially traverse is pointing to the root node. If traverse arrow key is equal to yes, yes is the node which we want to check. S is the value that we want to check, key value we want to check. If traverse arrow key is equal to yes, then return traverse, because this is the node which we are searching for. Else you check if s is less than traverse arrow key. If s is less than traverse arrow key, then just do traverse equal to traverse arrow left child. Okay, this if else it's not required, just I wrote, just I am writing if traverse arrow left child not equal to null, then traverse equal to traverse arrow left child, else traverse equal to null. Okay, otherwise directly also you can say traverse equal to traverse arrow left child. Okay, because at last it will be null, at one point it will be null, right? So if this first condition is not satisfied, then the second condition will be satisfied, because if s is first is it equal, we have checked, then we have checking whether s is less than key or not. Then obviously there is only one option which is greater than key. If it is greater than key, then you have to move in the right side direction, traverse equal to traverse arrow right child. So this if else is optional, you can remove. Okay, so like that it will go through the while loop. So if the if the value is found in some node, it will return a pointer to that particular node. Otherwise it will come out of the while and it will return traverse by the time traverse will be holding null. Okay, right? So this is how insertion is done. Okay, deletion logic I am not going to explain, I want you to implement by yourself. So there are three cases which we have discussed, right? Deleting the leaf node, deleting the node with one child, and deleting the node with two child. So that it's left as a homework. Okay, so so in the main function what I am doing is, first I am creating a BST and I am displaying the in order traversal. Then I am asking the user to enter a particular node to be searched. So it will take that key value and it will check using this SR pointer. It will call just search of yes, and if the node is available, a valid pointer will be returned that will point to the node which contains this particular key value. Otherwise it will return null. So here we are checking if SR is not equal to null, then we say that the node with the given key is available. Otherwise we say that the node with the given key is not available in the binary search tree. Then I am asking the user to enter the key of a node to be inserted and taking that as an input. Okay, and pausing that to insert. Okay, so which will insert a new node to the binary search tree. So after inserting that node, we are displaying again the binary search tree in order form, right? Then I am asking the user to enter the key value of the node to be deleted. So again we take an input, right? Then we call the delete. For delete I am passing the root node also, because why I am passing two parameters for delete, in the sense actually you don't know what node to be deleted. Okay, you don't know what node to be deleted, right? So you have to find, for example, if the node to be deleted has two children, then you have to find the what do you call, you have to find the next infix successor you have to find. Okay, or you have to find the infix predecessor. Okay, so infix successor if you want to find, then you have to use the right child. Using that right child you have to find. Okay, so you need a pointer to a particular node and also the value, right? So after deleting, again I am displaying the updated tree in order format, right? So let me compile this code and show you the execution. gcc bst.c -o bst. It's asking enter the number of nodes. So let me take some sample tree. With that we will give the input. Let us assume this particular tree. Okay, so if you see this tree, how many nodes are there? 1 2 3 4 5 6 7 8 9 nodes. So 9 nodes are there. let me take a copy of this. Okay, 9 nodes, so I'll give 9, right? So what is the order? I'll give 30 first, 30, then I'll give 15 and 7, 22, 17, 15, 7, 22, 17, yeah, then 27, 27, then 60, 45 and 75, 60, 45 and 75. Okay, so then it displays the in order traversal. You can see it is in ascending order: 7, 15, 17, 22, 27, 30, 45, 60, 75. Okay, then it is asking to check whether a particular node is existing or not. So let me give 60. So it says that the node with the key 60 is available in the BST, in the binary search tree. Okay, then it is asking enter the key of the node to be inserted. So say that I want to insert a node, say 100. Okay, so let me insert 100. So after inserting 100, this is the updated tree. Okay, so 100 will come as a right child of 75, I guess. Yeah, it will come here. Okay, 100 will come here. Okay, so that is the one which is displayed at last, right? Okay, okay, then it is asking the enter the key of the node to be deleted. Say I will give this 30 as the key to be deleted. 30 has two children, right? I mean, it has two children, 15 and 20. Here I used the logic for replacing 30 with infix successor. I have not used predecessor, infix successor. Okay, so infix successor means from the right subtree you have to find the minimum node, the node with the minimum value. Okay, from the right subtree, which is the node with the minimum value. What is the node with the minimum value? Obviously whichever is in the right subtree, whichever is in the left side. Okay, so this would be the node with the minimum value, right? 45. Okay, so it means this 45 should come here, this 30 should be replaced with 45, and again you have to check 45 how many children it has. This case it has no children, so just you can remove this, free the space for 45, and this left pointer of the 60 will be pointing to null, right? Okay, so let me give the node to be deleted as 30. So 45 should come there. Okay, so you can see here 45 is coming here, right? Okay, so this is the logic. If you want, I will show you the code for the, so for deleting you should find the minimum node in a particular tree. Okay, either in the, I mean you have to find the minimum node in the right side of a given node. Okay, so for that I have used a function minimum. Here you can see minimum. So this function it just takes a pointer to a particular node. Okay, it need not be always root node. For example, it can be this node, it can be 60. If it is 60, for 60 what is the minimum, it will check. Okay, right? If it is 15, for 15 what is the minimum, it will check. Okay, so whatever the node you pass, for that node it will, I mean starting from that node it will check what is the minimum, right? Okay, so what we do is you have to always go in the whatever the given node, from there you have to go in the left side, that's all, nothing else. So it's very simple logic. So that, I mean whatever the node we are getting as input, that is stored in traverse, and while traverse arrow L child not equal to null, traverse equal to traverse arrow left child, you keep on moving. Okay, finally you will reach, if it is 15, finally you will reach 7. When you reach 7, its left child is null, so it will come out and then return traverse, right? So this is required for deleting. Fine, let us stop here. Thank you.